As you can see behind me, the sheer scale of the operation is immense. This development promises to transform the region's industrial capacity.
The Russia-Iran Canal, a 700-kilometer steel and water artery connecting the Caspian Sea directly to the Indian Ocean. Forget the Suez. This project represents the ultimate physical test for modern infrastructure and human engineering limits. The primary challenge is not political, but a ruthless physical constant, 28 meters below global sea level. That is the elevation of the Caspian Sea, requiring a massive hydraulic lock system with unprecedented pumping capacity. Construction demands slicing through the Alborz Mountains, where the planet's hardest igneous rock formations currently stand guard. To conquer this strata, we deploy specialized drill bits armored with polycrystalline industrial diamond coatings for maximum penetration. However, the greatest enemy is thermal. Iranian deserts reach 50 degrees Celsius, causing critical deformation in standard metal components. Our solution is an ultra-high-pressure lubrication and cooling system, injected directly into the drill's combustion chamber. Every liter of coolant is calculated to absorb kinetic heat the microsecond the drill contacts the igneous magma rock surface. Inside the B3 cleanroom, hypersensitive flow sensors are assembled to monitor every cubic millimeter of water movement. Any assembly error in this lock system leads to catastrophic structural failure due to extreme thermal stress. We are not just digging a canal. We are manufacturing a massive transcontinental hydraulic regulation machine. The steel for the lock gates is a specialized anti-corrosion alloy, fatigue-tested in high salinity environments for decades of survival. Look at the blueprint. This is Phase 1, where 200 million cubic meters of earth will be displaced. Phase 1 begins with the mobilization of a fleet of heavy-duty TBMs, specifically modified for high-torque rock shearing. These machines must sustain constant operation while internal temperatures are regulated by secondary liquid nitrogen heat exchangers. The logistics of moving these 4,000-ton cutters across the Iranian plateau requires the construction of temporary heavy-load railways. Every joint in the TBM's main bearing is monitored by infrared sensors to detect microscopic friction anomalies before they escalate. As the cutters penetrate the first 10 kilometers, the material shifts from loose sediment to hyperdense metamorphic basalt. This is where the A3 class mining machines demonstrate their dominance, applying over 10,000 tons of thrust force. Simultaneously, a massive muck removal system utilizes high-speed automated conveyor belts to transport debris at 60 kilometers per hour. Engineers on site, classified as CHAR 2, perform ultrasonic structural integrity scans on every newly exposed rock face every hour. They are looking for microfissures that could indicate catastrophic groundwater ingress from the Caspian's high-pressure subterranean aquifers. The heat rejection units are now operating at 95% capacity to counteract the geothermal gradient of the deep crust. In the control center, data from 10,000 telemetry points is processed in real time to adjust the drill's RPM. We are observing a phenomenon of thermal expansion in the main cutter head, precisely as predicted in our B3 simulations. To mitigate this, the lubrication pressure is increased to 500 bar, creating a microscopic film between steel and rock. The operational cost of this single maneuver exceeds $100,000 per hour in energy and synthetic lubricants. But the result is a perfectly cylindrical shaft, the foundational geometry for the world's most advanced inland waterway system. With the primary shaft stabilized, we initiate the casting of the reinforced concrete lining using high-strength sulfate-resistant cement. This specific mixture is engineered to withstand the aggressive chemical erosion from the high mineral content of the desert soil. Automatic slip-forming systems crawl along the tunnel walls, pouring concrete at a constant rate of 5 meters per hour. Precision sensors embedded in the wet concrete monitor the curing temperature to prevent any internal thermal microcracking. Next, we move to the installation of the lock gates, colossal structures weighing over 3,000 metric tons each. These gates are fabricated in segments at our specialized metallurgy plant and transported via modular self-propelled transporters. The alignment process requires sub-millimeter precision, utilizing satellite-linked laser leveling systems across the entire lock chamber. Char, 2 engineering crews supervise the high-tension bolting of the hinge mechanisms, using hydraulic torque wrenches at maximum capacity. To ensure long-term durability, every steel surface is coated with a multi-layered ceramic polymer hybrid for extreme saltwater protection. The hydraulic power units responsible for moving these gates are now being tested under a simulated load of 500 bars. We use synthetic biodegradable fluid to minimize environmental impact in case of a high-pressure seal failure during operation. As we reach the mountainous sector, the excavation shifts to a drill and blast sequence for the massive water bypass tunnels. Each detonation is precision-timed, using digital initiators to minimize the shockwave impact on the existing canal structural walls. After every blast, automated robotic arms scale the rock face to remove loose fragments and apply quick-set shotcrete. The scale of this operation consumes over 500 megawatts of power, supplied by a dedicated high-voltage substation grid. Energy management is critical. We utilize massive capacitor banks to stabilize the grid during peak drilling torque cycles. The canal floor is now being reinforced with a triple-layer geomembrane to prevent saltwater seepage into the local desert aquifers. Each seam of the membrane is thermally welded and vacuum tested to ensure a zero leakage tolerance across the entire 700 kilometers. In the Central Valley, we are constructing the world's largest ship elevator, capable of lifting Panamax-class vessels 60 meters vertically. The counterweight system alone involves 12,000 metric tons of high-density concrete and precision-forged steel cables. Char, 2 technical teams are now calibrating the synchronous motor drives that ensure the elevator remains perfectly level during transit. A deviation of just 5 millimeters could trigger an emergency structural lock, halting all maritime traffic through the artery. Meanwhile, the dredging fleet at the Caspian entrance is processing 10,000 cubic meters of silt every single hour. Specialized suction cutter dredgers use tungsten carbide teeth to chew through the compacted marine sediment of the northern coastline. All dredged material is transported via a pressurized slurry pipeline to a designated reclamation area for industrial land creation. Environmental sensors monitor the turbidity of the surrounding water, ensuring the project adheres to strict Caspian ecological protocols. The scale of the logistics chain is mind-boggling, requiring 24-hour operation of our automated heavy-lift drone fleet. They deliver critical spare parts to remote mountain sites where traditional ground transport would take days to navigate. Every component, from the smallest bolt to the massive lock gates, is tracked via a real-time digital twin.
As you can see behind me, the work here at the mountain pass is proceeding rapidly. The rock extracted by these 70-ton trucks is being used to build...
Post-excavation stability is our next priority. We are injecting high-pressure polyurethane resin into the rock fissures. This chemical grouting creates an impermeable shield, preventing acidic mountain runoff from corroding the canal's concrete primary lining. High-altitude logistics require our CHAR, 2 teams to operate specialized heavy-lift helicopters for placing the modular ventilation towers. These towers are essential for clearing diesel exhaust from the massive service tugboats that will traverse this subterranean section. Every tugboat is equipped with a dual-fuel propulsion system, optimized for high-torque maneuvers within the narrow canal confines. In the arid Lut desert sector, we face the opposite challenge: extreme evaporation rates threatening the canal's water levels. Our solution is a series of automated solar-powered shading structures that double as a massive renewable energy farm. These panels track the sun with astronomical precision, reducing water loss by 40% while generating gigawatts of power. The electrical energy is fed back into the main pumping stations, creating a self-sustaining hydraulic loop across the desert. As the canal nears the Hormozgan province, the terrain transitions into complex salt domes requiring specialized boring techniques. Salt is highly abrasive and structurally unstable. We utilize a saturated brine drilling fluid to prevent premature dissolution. Char, 2 specialists monitor the salinity levels in real time, ensuring the chemical balance protects the TBM's internal mechanical seals. The canal walls in this sector are reinforced with fiberglass polymer rebar, a material completely immune to salt-induced oxidation. Every kilometer of the waterway is equipped with underwater acoustic sensors to detect potential structural shifts or leakages. This data is relayed via a fiber optic backbone to the central command, where AI-driven models predict maintenance requirements. Integration of the SCADA control system begins, linking every hydraulic valve to the primary neural network core. The software architecture is redundant, utilizing 3 independent processing nodes to eliminate any possibility of a system-wide blackout. CHAR. 2 technicians are currently executing dry run simulations, cycling the lock gates without water to verify mechanical clearance. We observe the silent movement of 3,000 tons of steel, pivoting on bearings lubricated by high-viscosity synthetic grease. Next, the canal bed undergoes a final vacuum sweeping process to remove any metallic debris that could damage ship propellers. Precision magnetism arrays are dragged along the bottom to capture microscopic ferrous fragments left behind by the TBMs. Water flooding phase 1 commences. We draw the first 1,000,000 cubic meters from the Caspian via a controlled intake. The sound of rushing water is monitored by seismic sensors to ensure the flow rate doesn't cause cavitation or erosion. As the first lock chamber fills, we analyze the structural deflection of the concrete walls using laser interferometry. The data shows a displacement of 0.2 millimeters, well within our strict safety margin for catastrophic structural load. Simultaneously, we test the air injection system designed to reduce water friction for high-speed transit of lightweight vessels. Microbubbles are released from the canal floor, creating a gas cushion effect that significantly lowers the drag coefficient. This innovation allows for energy-efficient transport, reducing the total carbon footprint of the entire logistics chain by 30%. Teams on the surface deploy automated boom barriers to manage surface tension and prevent debris from entering the locks. The canal is no longer a trench. It is becoming a living, breathing machine, ready for its first maritime test. We initiate the high-load transit test using a decommissioned supertanker ballasted to simulate a full displacement of 300,000 tons. The vessel enters the first lock chamber under the precise guidance of our automated laser docking system, maintaining a 0.5 knot approach. Pressure sensors along the hull contact points monitor the hydrodynamic interaction between the ship's skin and the canal's reinforced concrete walls. As the massive gates close, the hydraulic pumps begin the lift sequence, moving 400 million liters of water in 12 minutes. The turbulence within the chamber is neutralized by our patented honeycomb diffuser floor, preventing any dangerous vessel oscillation during the ascent. Technical divers are stationed at the base of the lock to perform real-time visual inspections of the lower seal integrity. They utilize high-definition sonar cameras to penetrate the sediment-heavy water, searching for any signs of high-pressure cavitation damage. In the desert sector, the focus shifts to salinity management as we begin the permanent replenishment of the canal's middle sections. A series of desalination plants powered by the solar canopy work at peak capacity to maintain the water's chemical equilibrium. The salt byproduct is mechanically harvested and processed for industrial use, creating a circular economy within the project's infrastructure. Night operations are illuminated by our energy-efficient LED array, casting a clinical white light over the entire 700-kilometer artery. Every bridge crossing the canal is equipped with dynamic weight sensors to detect structural fatigue caused by heavy logistical transport. These bridges use a cantilevered steel design, allowing for the maximum vertical clearance required by the next generation of container ships. The integrated weather stations now relay real-time wind speed data to adjust the tension of the vessel mooring robots automatically. We are observing the perfect synchronization of mechanical force and digital intelligence, a testament to our manufacturing precision. Final system diagnostic. All 320 hydraulic locks report a synchronized pressure variance of less than 0.1%. The automated traffic control AI now takes command, sequencing the transit of the first commercial convoy from the Persian Gulf. This corridor reduces the transit time between Mumbai and St. Petersburg by 20 days, bypassing the congested maritime bottlenecks of the West. As the lead vessel clears the final lock at Bandar Abbas, we observe the perfect displacement of salt water back into the ocean. The ecological barrier systems are activated, utilizing electromagnetic fields to prevent invasive species from migrating between the two water bodies. Engineering teams perform the final ceremonial torque check on the project's commemorative foundation bolt, made of gold-plated titanium. The operational data is now being shared with global logistics hubs, recalculating the supply chain efficiency for the entire Eurasian continent. Beyond transport, the canal's integrated desalination network begins supplying 2 billion litres of fresh water daily to the arid provinces. We have transformed a barren wasteland into a high-tech industrial oasis, powered by the sun and regulated by cold, hard logic. Maintenance robots are deployed into the primary shafts, starting their permanent 24/7 patrol of the canal's structural integrity. The cost of $16 billion has been justified by a projected annual revenue of $3 billion in transit fees alone. This is not just infrastructure. It is the ultimate manifestation of human kinetic energy directed toward a singular civilizational goal. Factory Machine Lab has successfully closed the loop between geographical impossibility and mechanical reality on a planetary scale. The gates are open, the sensors are active, and the new Silk Road of the 21st century is now officially operational.
Since its expansion, this canal has dramatically reshaped global trade routes, cutting transit times by nearly a week for ships heading east.